section we need to think about how can we reduce some of the less reactive types of carboxylic acid derivatives. So amides have the most resonance contribution from the lone pair on these nitrogen atoms. And since this contributes to lowering the ground state energy, it's hard to add nucleophiles in. So in order for us to reduce primary amides, we're going to use very reactive species, such as lithium aluminum hydride. We're going to, and after these reductions, we actually get a product we're not used to seeing. We're just seeing a leaving group off of the carbonyl go away, but in this case, the nitrogen functionality is retained. So if you have a primary amide, it will turn into a primary amine. If you have a secondary amide, it'll turn into a secondary amine. And a tertiary amide will turn into a tertiary amine. And so the hydrogens that get incorporated are actually coming directly from the lithium aluminum hydride. Each of these hydrogens come from LAH itself. And so we can see that these red hydrides are directly incorporated at these positions. And looking at the mechanism, these get a little bit funny. So we're going to go through this hopefully slowly. The beginning is very similar to what we've seen before. I'm just going to draw methylacetamide here at the beginning as a model primary amide to show these possibilities. We're going to draw out the aluminum hydride anion. And the first step is going to be very similar to how we've seen things like carboxylic acid derivatives get reduced. We're going to have a nucleophilic sigma bond attack the carbonyl, and this will give us a tetrahedral intermediate. So this initial tetrahedral intermediate has aluminum attached to the oxygen. Sometimes we draw this just as an ionic bond, but in this case it's fairly useful to look at the counter ion in this fashion. And there's actually two ways that we can imagine the breakdown of this tetrahedral intermediate. Similar to the other examples, these tetrahedral intermediates will be unstable and they will collapse back to sp2 hybridized systems. Following what we've seen before, we could just have the lone pair of this nitrogen directly kick out the aluminum leaving group. And this is a little bit unusual because we end up with some fairly reactive species. Along the way, we end up with an iminium. This iminium is both very electrophilic but also quite acidic. These hydrogens on the nitrogen are quite acidic, and we're under conditions with very strong nucleophiles, so lithium aluminum hydride is also very basic. And now we've also made something that has two negative charges right next to one another. This is why I said this is somewhat uncomfortable. So we're putting two negative charges. Electrostatically, this is very frustrated. This isn't as bad as some other situations since the aluminum now has gained a full octet, so a negative charge on aluminum isn't quite as high energy. But now we can see that actually an acid-base reaction can happen very quickly, where each of these hydrides are also quite basic. We have these very acidic hydrogens on the amine structure. Along the way, we're going to lose hydrogen gas. This will just bubble away out of solution. And we know from studying these reactions that hydrogen gas is in fact evolved. Did we get an imine along with this aluminum hydride byproduct that has a formal negative charge? In these reactions, we always have an excess amount of aluminum hydride, or it could be one of the other active hydride species that are still around. But we can just say lithium aluminum hydride again. This will do another addition into the carbon-nitrogen double bond. And we end up finally with this aluminum hydride minus on the nitrogen, and we successfully introduced both of those hydrogens that we needed to bring in. The final step is simply just adding a little bit of workup. Water will do the trick. It could be a little bit acidified, but we don't necessarily want to add too much acid so as to protonate the amines unless that is going to be desirable. So that gets us to the product. There is actually a slightly lower energy way to draw this conversion of the breakdown of this tetrahedral intermediate, and it effectively does both of these two steps at once. Since we can make a cyclic structure, we can Let me just copy and paste this again. We're going to make a little side note over here. Well, now we're going to change the arrows a little bit. Instead of having the nitrogen lone pair kick out that aluminum oxide, we can kind of imagine this already being somewhat basic. This aluminum hydride can take this hydrogen at the same time as this goes to form the imine bond and lose that O minus. This creates a cyclic transition state. So it's a six-membered ring, so it's fairly favored. And this would directly give us the imine minus H2 gas and also that same aluminum byproduct we had before. It's thought that this probably happens in a more concerted fashion. If it helps you to draw out the stepwise process to keep track of proton transfers and leaving groups, that is just fine too. But just to show you another alternative how we can avoid some of these high energy intermediates. Something that ends up being a little bit more difficult to avoid is actually whenever we have a tertiary amide. So whenever we go and have a tertiary amide, we end up with slightly different scenario. So I'm going to draw the addition product from a tertiary amide. And quickly, I think you can see where the issue comes. So instead of having hydrogens on this nitrogen that can be deprotonated, we end up with an intermediate that does not have anything that can be deprotonated. So acid-base chemistry really can't take place. In this instance, we are kind of forced to go through this process where we're going to ionize this bond. The lone pair from the nitrogen will kick out the aluminum oxide. We end up with an iminium again, but now it's not acidic at all. It's just very electrophilic because we don't have any hydrogens that can be deprotonated. And so this can directly reduce the iminium and once again give us a tertiary amine. Note that in these reductions, this is not easy. These don't happen at room temperature. Usually we have heat added along the way. Heat is needed to achieve either these intramolecular eliminations or these high energy charged intermediates to proceed. And along the way, something to certainly keep in mind, the reason that the nitrogen acts to kick out this aluminum group is that a nitrogen is a much better lone pair donator. So in the end, the oxygens won't be leaving, the nitrogens will be retained, and these further get reduced to simply give amine derivatives.